I'm the coordinator of the WP2, the work package 2 of the Perceive project, which is responsible for the training program. Inside the training program, we planned a series of webinars that started in April and will finish in October. And today we are at the third episode of this series of 10, dedicated to the subject of color change in sensitive artistic and historical collection, and the use of advanced research and innovative methodologies for their studies. The objective of Perceive is to enhance the digital capabilities of scientists and cultural institutions through a service-oriented AR architecture and toolkit, while also developing a new design theory for both on-site and remote VR/AR experiences. The complexity involved in their study, particularly in reconstructing the original appearance alongside the imperative of effectively communicating these aspects to future generations, remains a critical focus. All the episodes of our webinar are organized with two speakers who will address the same topic from two different perspectives, followed by a question and answer session at the end of the presentation. We really care about your feedback and interest, so to enrich the discussion, please write questions in the chat. The speakers will be happy to answer at the end of their presentation. Today, we are featuring MuLaX, a groundbreaking Web 3D application designed to map and discover diagnostic processes behind studies of lost polychromy and color changes in colored collection within museums. MuLaX is an innovative tool that allows users to visualize, inspect, manipulate, and compare analytical and color layers directly on a 3D model of the artwork. Built on the open source Atom framework, MuLaX supports the interactive exploration of analytical analysis through a sophisticated annotation system for spot analysis such as microscopy, XRF, and force, and it also offers a multi-layer visualization for imaging technique like VIL, UVL, accessible both thanks to lenses and split models. The speakers of today are Daniele Ferdani and Bruno Fanini. Daniele Ferdani has a PhD in archaeology. He is an expert in digital archaeology. His research focuses on the development of integrated methodologies for the reconstruction of classical and medieval contexts and their communication through virtual museum and virtual reality systems. Daniele has very intriguing skills: 3D modeling, 3D image processing, 3D visualization, archaeological analysis of ancient architecture. Bruno Fanini holds a PhD in computer science and he is a researcher in the Institute of Heritage Science at the National Research Council. He is part of the Digital Heritage Innovation Lab, and his research and development activities focus on real-time 3D graphic, immersive visualization, natural interaction, and design of 3D user interfaces. He has designed and developed open-source Web 3D tools such as the Atom framework, serious games, virtual museum, and interactive application targeting cultural heritage. Before we begin this webinar today, let me remind you of the next episode that will be in June 17 at 11 a.m. Rome time. The title is Orthogram, Revolution and Realities, Digitization, Separation and Restoration. The speakers will be Giorgio Trampi, Associate Professor at the Norwegian University of Science and Technology, and Kathleen Langford, Curator, Writer, and Researcher specialized in photography. We invite everyone to participate actively and contribute to the dissemination of this initiative. To stay up to date, please visit our social channels: LinkedIn, Facebook, YouTube, X, Instagram, and of course our website. You will find all the links in the chat. I also wish to remind you that this webinar is recorded and that the video will be available on YouTube channel on the Perceive project website. Thank you for your support, and we hope to see many of you at the upcoming events. Please, Daniele, you can start your presentation. Thank you.
Thank you, Cristiana, for the nice presentation. Let me share my screen. Thank you so much. Welcome, everyone. My name is Daniele Ferdani. I'm senior researcher at the CNR. And today we are going to introduce you the MuLaX tool. In this first part of the presentation, I will mainly focus on the development process behind the multi-layered 3D model. And following my talk, my colleague Bruno Fanini will explain better and will delve into the tool functionality and user interface in a greater detail. So just let me briefly introduce the tool. So what is MuLaX? MuLaX is an innovative Web 3D tool developed within the Perceive project. And it is designed to offer both expert but also the general public an interactive platform to explore and analyze cultural heritage artifacts, in this case ancient statuary. So the tool enables the visualization of 3D model, and these 3D models are enriched with data coming from archaeometric analysis, coming from diagnostic. And this data reveals traces of ancient polychromy. So this tool is built on the open source Atom framework, and my colleague Bruno Fanini in the second part of this presentation will explain better what is Atom and what can do. And so MuLaX facilitates this interactive exploration of this analytical result using annotation system and spot analysis. It uses multi-layer visualization for imaging techniques like VIL, visible induced luminescence, and UVL, ultraviolet light-induced visible luminescence. So here you have just a preview of the interface that my colleague will explain better later. So in order to test the tool with a practical case study, we choose this particularly interesting artifact, the so-called Venus in a bikini. It's a Roman statue discovered in Pompeii, and now it's conserved at the Man Museum, the National Archaeological Museum of Naples. These statues, as you can see here in this picture, show the Venus just before the bath. With the right hand is unfastening one of the sandals, and the nicknames Venus in a bikini comes from the golden strophion, this band that cover her chest, and this chest looks like a modern bikini, so that's the reason of the name. So here you have a brief description of all the digitation workflow. So this ad hoc workflow has been developed to digitize complex artifacts like this one and create multi-textured 3D model that can be integrated into the Web 3D app. So this process includes different steps from digitization using photogrammetry, photogrammetric computation, integration of different photogrammetric data sets, so not only visible imaging, but also spectral data set like UVL and VIL. And finally, post-processing using computer graphic software in order to optimize the meshes and the texture for Web 3D implementation. So now I'm going to better explain in detail this digitization workflow that we use to create this multi-layered model. Okay, so first of all, independent photogrammetric acquisition for each spectral band were performed under controlled light conditions. So, for example, for the visible data set, here you have the camera used, the Canon L6D with a 35mm lens. And it was mounted on a tripod in order to make the camera stable. And we operated the acquisition inside a light box. The light box was equipped with a LED light in order to minimize reflection and shadows and make the light diffuse. So the artifact was placed on a turning table that you can see here, and the turning table features encoded photogrammetric targets to ensure at the end of the process in precise scaling and alignment, and also to check the accuracy of the final 3D models. So images were then captured by rotating the turning table, and the camera was placed at different eye and angles in order to capture close-up picture from different elevation and different angles. On the other hand, here you have the acquisition schema for UVL and VIL imaging. In this case, we used two different cameras, and the camera were combined with flashes equipped with specific spectral filter. These spectral filters was used to provide correct wavelength emission, and specific lens and filters were applied to isolate the different spectral phenomena. So here you have an example of the different kind of filter used both for the flashes and for the camera. So three different acquisition datasets were performed on the statue. So after the acquisition, the images were then processed in order to enhance detail, visibility, and uniformity. So in this case, a pre-processing, we in Lightroom, exposure, contrast, lighting, and shadow, white balance were carefully adjusted, and in particularly for the UVL and VIL dataset. And this was really important to compensate the lower native brightness and contrast. So after that, each spectral dataset was independently processed using a photogrammetric software. In this case, we used 3DF Zephyr in order to generate aligned camera position, dense point cloud, texture mesh, and so on. This is the standard photogrammetric workflow to obtain the model. And for the visible dataset, the ground control point were used in order to scale the model and to check the accuracy of the final model, and to get the root mean square error, okay, which was very low, around 1 millimeter. So the next step was to match all the data set together. Okay, so integrate all the three different photogrammetric data set, VIL, UVL, and RGB in the same space, in the same workspace. So to bring this three spectral model into a common spatial framework, we use a specific tool of 3D Zephyr that allows to import different workspace together. We use 4 different control points placed in each workspace with the same name in order to use them as a matching point in order to align the different data sets. And thanks to this process, we correctly aligned and positioned the different photogrammetric workspaces relative to each other. And this is really important because this means that not only the point cloud and the meshes are aligned, but also the other photogrammetric metadata, like the camera position, internal parameter of the camera. All these metadata remain consistent after the registration with the model. So in this way, preserving this metadata is essential for the subsequent phase, which is texture projection. So by maintaining the original relationship between the images and the 3D model geometry, the subsequent texture building and at the end we get these final results. So the spectral dataset were projected onto the high quality visible mesh using the consistent UV mapping, because all the three meshes share the same UV mapping, and this ensured that the multi-band texture were perfectly aligned spatially. And this allowed then in MuLaX to dynamically explore and switch between different textures. So after this step, of course, the different 3D models with different texture obtained were very high resoluted, both in terms of geometry, around the number of polygons was around 28 million, and in terms of texture resolution. All of this model has 5 texture, 8 key textures, so very high resoluted. So in order to optimize both the meshes and the texture for real-time implementation, because MuLaX is a Web3D online tool, so we had to optimize the mesh. So these models were optimized for this Web3D dissemination, and then through the integration into the Atom framework, by reducing the poly count. So the high resolution model was reduced in 3DF Zephyr. So the number of polygon was reduced from 28 million to 300,000 polygon. And then after this after this poly count reduction, the retopology was performed using Instant Mesh, another software that can be used to convert the decimated triangular mesh into a quad dominant mesh. This kind of quad dominant mesh can be used easily in computer graphic software like Blender. So as you can check the two images, you can see that in the first image, the topology is an irregular triangulate network. In the final optimized model, the mesh is a quad dominant mesh. So the topology has been reorganized in a regular way. And in this way, the model can be easily handled in a computer graphics software like Blender. So once imported into Blender, the model was subsequently manually segmented into 3 main blocks. Okay, the blocks were homogeneous, so it means that each block covers an area of approximately 0.15 square meter. So they are uniform in terms of area. So, and for each block, a dedicated shader and UV map were created. So instead of using the automatic UV mapping created by photogrammetric software like 3DF Zephyr, in fact, this kind of software typically produces fragmented layouts impossible to be edited by 2D software like Photoshop. So instead of using this kind of automatic unwrapping, we use the manual unwrapping in Blender. Okay, so by carefully placing seams line, it was possible to generate these logically organized UV islands. optimize the UV space distribution, like in this case, control the padding, and minimize the wastage of the texture. So as you can see in this image, the texture space has been optimized. And also the padding. The padding is a sort of buffer of duplicated or extended pixel data added around the edges of the UV island. And this helps to prevent visual artifact in the 3D model visualization, like seams or color bleeding. So this kind of element can be controlled manually in Blender, giving us the possibility to control and improve the final result. And here you have an example of the final result. So this optimization allowed to obtain an average textile density of approximately 170 pixels per centimeter. So the textile size is around 0.05 millimeters, so very, very detailed. And we use 3 different textures to map the entire model. So this ensured high fidelity in the visualization of the surface detail. So, and also you can see the texture image generated by the photogrammetric software. As you can see here, the pixel distribution is a mess. Is not easily usable in computer graphics software, and there is a lot of wastage of space. In the manual UV mapping, the different islands are well organized. The space wasted is reduced, and you can see also the padding around the texture island. So in this way, we could optimize all the textures. And this optimization was performed for all the texture layers, maintaining the same UV coordinates. As you can see, all the 3 different textures, visible, UVL, and VIL, share the same UV mapping. You see, the same elements can be found in the same position in the 3 different textures. So after that, we also improved the texture in order to make the final model, the visible model, more realistic in 3D visualization. So we improved the texture. So after the UV unwrapping, the optimized model was exported in OBJ format and re-imported in the photogrammetric software, 3ds Zephyr, allowing us to maintain the manual UV mapping and automatically generate the texture, the high resolution texture. And furthermore, in Zephyr, we could generate the normal map using the original 28 million polygon, the high quality model, as source. And this enabled the optimized Web 3D version to simulate the perception of the complex surface detail of the original model. I said before that in order to optimize the geometry, I need to reduce the poly count from 28 million to 300,000 polygons. But reducing the number of polygons, as you can see here, you lose the fine detail of the surface. In the original model here, you can see the tool marks on the marble surface. In the optimized model, these details are lost. But generating the normal maps using a standard workflow, it was possible to simulate on the optimized model the fine detail, the fine surface detail. In this way, the model was further optimized. And finally, we used the standard PBR texturing workflow, the physically based rendering workflow. So this workflow is aimed at achieving realistic visual responses under dynamic light condition. So that means into practice that the final model simulates the physical behavior of the real artifact. So starting from the diffuse image is the one that simulates the color. It was possible to derive metalness map and the roughness map. The metalness map tells the rendering engine how the light should interact with the surface, and specifically if that pixel should behave like a metal material or not. So black means not metal, white means metal. On the other hand, the roughness map simulate the micro surface scattering effect. Okay, so here you can see the difference. In the first image, we have only the model with color and normal maps. And in the second image, you have a complete PBR 3D model, so with metalness and roughness. And here you can see that in real time, we can simulate reflection of the gildings, so and also of the marble. So in this way, it is possible to simulate different response to the light of the different material. So in this way, it was possible to generate a realistic 3D model to be used and imported into Atom and in the MuLaX tool. Okay, so that's all for my side. I hope that everything was clear, but we will have time in the Q&A session if you need more explanation. So I leave the stage now to my colleague Bruno Fanini that will explain better the next step and the integration into MuLaX tool. Thank you, everyone.
Okay, so good afternoon. Thanks Daniele and also Cristiana for the invitation. I will also share my screen. Okay, so in this second part, we'll dive into more detail into what is the MuLaX tool. First, just a very quick background regarding, of course, the advancement of Web 3D technologies that nowadays allow us to create more and more advanced tools to interact with such, as you saw from Daniele, with such complex data that is, of course, scientific data. And so for this project specifically, we started from a few goals. So this is the origin of the tool. First of all, of course, we focused on the idea of this discovery of invisible or lost information on this 3D collection. Then, of course, to improve the readability of the artwork. And then, of course, investigation of new ways to access and inspect such multidimensional artworks directly online through a standard web browser for experts, but also for the general public. This, of course, led to a few requirements that, of course, range from novel interaction models, for instance, then cross-device access, so different device to access interactively the tool, flexibility, so for instance, to embrace different scenarios, integration with different workflow, like you saw also from Daniele, and in general from other workflow in the Perceive project. And then another requirement was, of course, the use and exploit discovery approaches that are accessible and expressive. So for this specific point, we start, of course, from existing literature, in particular the interactive lens metaphor that we already used a few years ago for for other projects, like you can see from the video. In this case, we are discovering something that is lost. This is a temporal dimension that we are using here with this interactive way to discover something that is not there anymore. And then, of course, this technique was that is already proven in literature for the engagement also for general public. We evolved this technique also for diagnostic-oriented projects. Here, just a few examples with Brancassi point of view project and Codex 4D, both involving the discovery of invisible information. So how to create such a tool? As Daniele anticipated, this tool is based on Atom, that is an open source framework that allows you to create very rapidly this Web3D or WebXR tools, application, or experiences for heritage science. Is modular, so you can actually pick the pieces that you need for that you actually need for creating such a tool. It's a framework that is already used in several national and international projects, and especially is based on very large open ecosystems and international web standards. So this is also especially important for interoperability. Okay. So at this point, what is actually MuLaX? So MuLaX, as you already, as Daniele anticipated, is a tool that is completely online. So you just need a web browser to access this tool for the interactive discovery, also immersive discovery of diagnostic processes on multi-layered collections. Of course, is based on Atom. Is cross-device, so that means that you can use a very wide range of devices to for the actual inspections. You can use a smartphone up to desktop device, kiosk, museum, up to XR devices, as we'll see in a few moments. Very important to say that this is the result of a very high multidisciplinary work that involved conservation scientists, modelers, developers, UI UX designers, and so on. This is very important for what we actually obtained. MuLaX supports the inspection of multiple items and offers advanced features that will go now more into detail. So first of all, there is the possibility to enrich the item with this point of interest that are actually annotations that are can have different categories, like for instance spot analysis, like anticipated from Daniele, that are microscopic or punctual measurements, or imaging data like ultraviolet or VIL. Then each of these point of interest can have also one or multiple techniques associated. And as you see also from the video here, in MuLaX, there is also the possibility to live filter directly these annotations by category or by techniques. And also another important feature is that each of these annotation stores also the expert defined view. So when the user clicks on one of these annotation, the original view from the expert is recalled. So moving on, this is of course one of the most prominent feature of MuLaX, that is multi-layer discovery. So as anticipated, it's as you can see, is an interactive discovery of analytical or color data in the form of layers, like you saw also from the Daniele presentation. Here we support multiple layers that can be as many as you want. Exactly also for groups, you can create groups, and so having multiple groups and each group with multiple layers. There is also this possibility of having this split mode, as you can see from the video, that actually came as an input from conservation scientists. And this led also to an extension of the original lens mode that we explored in the past. And this transformed into a fully mathematical model with discovery shapes, so that can be automatically adapted depending on a given formula. Of course, this way of exploring the item is fully compliant with the AR and with the augmented reality and virtual reality presentation modes, as we'll see also in a few seconds. Let's talk now about another feature that is offered by MuLaX, that are semantic masks that are mainly used for three different purposes. So the first one is to define very complex semantic arrays, as you can see here in an example of golden traces here in the top left, as you can see in black and white. They can be used also for selective transfer, so specific areas you can tweak style or color, as well as some parameters of the material. So you can use this mask for specific areas to tweak a bit the material parameters. So how then, the question is, how can we create this semantic mask? Well, one way is externally using other services, like including the services in Perceive. So, for instance, semantic segmentation services and other. Or in MuLaX, you can also directly create manually, as you can see from the video, using this model of interactive semantic painting. So you can use actually a very interactive way to create dynamically these semantic masks. And very important here to highlight that this way of is image-based way to create these masks, but also the multi-layer discovery, since it is operating on a texture space, of course, it fits very well also the 2D domain. So it was an effort to embrace also other domains and other scenarios, as we'll see also in the end of the presentation. So moving on, here is some example of XR inspection that is, of course, possible thanks to the use of underneath Atom framework that allows immersive VR and augmented reality presentation modes. And this led to, as you can see from the video, a very special inspection of the item. In this case, of course, the Bikini Venus. And you can perceive the full scale. You can explore the full scale replica right in front of you with all this complexity of data that you can explore here, as you can see from the video and also from these screenshots. This also led to another result that are this an adaptive toolkit with special user interface elements that automatically adapts depending on the XR device that you are using for MuLaX. And of course, all this is also using the existing best practice and the literature on such topics. So let's move for the part of integration. So how can MuLaX can be integrated in a cloud environment? So of course, as you saw, MuLaX is accessing an online collection with multiple items. Here we see the Bikini Venus, but of course there is the possibility to have hundreds of different items that of course include 3D models, but include of course discovery layers, semantic masks that we saw in the previous slides, but also multimedia content, for instance, for the annotations and much more. So in this sense, we can of course rely on a cloud integration, so cloud storage that we can access to upload all this data. And this data is actually accessed by both humans, teams that are maybe in a different locations that collaboratively access the cloud to manipulate this data, like for instance also 3D modelers and other experts and researchers, but also processing services. So could be like the example of the example that I bring before on some services that are dedicated to semantic segmentation, or some services that is maybe operating on the optimization of or some 3D models. So they can both operate on the same cloud cloud storage, and this, in this sense, this data layer. So MuLaX is, of course, an explorer, but actually the X in MuLaX stands also for extensibility. So in this sense, the tool is now growing, and beyond the original scenario that was the first one on polychromy on statues, and now we are exploring, of course, together with other partners in Perceive project, especially for scenario 2 that there are paintings, but also scenario 3 on textiles. This is an ongoing, of course, effort to evolve even more this tool. But also the idea is to provide a base for an extensible interaction, so something that goes beyond the virtual world and can provide access to from visitors, like for instance in public exhibits, to control remotely some features of MuLaX and some behaviors using their own devices or peripherals that are in the expo, for instance. Then we also explored the use of activators, so something that also, once again, in a public exhibit can be used to enable or switch on and off some specific components or features of MuLaX. We are also exploring the possibility of live color transfer directly on these artworks. And then, of course, there is also other possibilities, including the tangible user interface and much, much more. So this is the idea, to go beyond this the pure virtual environment and provide something that is reusable and extensible. So here is my presentation. Thank you very much, and hope there is some also hope it was clear, first of all, and then if you have questions, just let us know. Thank you.
Thank you, Bruno. Thank you, Daniele, for your very amazing presentation that introduced many of us to a world that for museum professionals or conservators or museum scientists is very far from our education system, because it's extremely important to work in multiple discipline equipe. And this is the example of how the different competencies are joined together and have great results. I think that MuLaX will be only the beginning of a new way of perceiving colors in ancient collection, in particular in statuary, because it's very, very helpful. So thank you again for your presentation. We have a series of questions. The first is, I relayed the question to both of you, except one that is specifically for Daniele. The first question is, what are the main technical challenges in creating a 3D model that integrates multispectral data, and how can they be addressed?
Okay, maybe I can answer this question. So there are probably the main technical challenge is the alignment of the different data sets. Especially, I mean, we adopted a flexible workflow. So as you can see in the presentation, we used 3 different cameras, and we performed the photogrammetric survey in different moments. This complicates the result, because using the same camera, maybe changing the filter on the camera, using the same tripod during the post-processing. This helps in maintaining the same relative position of the camera in the different spectral map. So the alignment phase works better. But sometimes, like in our case, it was not possible to use the same camera or to perform the acquisition at the same moment. So we firstly did the 3D acquisition in visible spectra, and then in a second step we did the UVL and VIL. So we changed completely the environmental condition, the position of the tripod, so it was impossible to keep the same initial relative position. So during the photogrammetric post-processing, we need to align the different data sets together. So in this way, we use specific tools that now are available in the photogrammetric software. So using common reference point, it was possible to merge the different data set. And we kept only the three-dimensional model generated by the RGB photogrammetry, because from a geometric point of view is the most accurate. And we used the photos coming from the other data set, like UVL and VIL, to project the color information on top of the model. So at the end, we have just one model generated from the photogrammetric RGB survey, but three outputs, so three texture outputs. I can show you here briefly let me check. Let me show you here the difference. So for example, this is the geometry generated by the RGB photogrammetry. As you can see, is pretty accurate. We have a great surface detail. And here we have the geometry generated by the UVL. So as you can see, it was able to reconstruct the shape of the statue, but there are a lot of inconsistencies in the geometries, like here, for example. So the quality of the mesh is not comparable with the one generated from photogrammetry. But the camera position that you have around the model are consistent. So we just have to import this data set and align it with this one. So, for example, in this 3D viewport, all the camera, RGB, VIL, and UVL are consistently aligned. So you just have to choose the data set you want to project on this one. And so you can generate different outputs. Okay, so here you have the red dot are the point that we use, the common point that we use to match the different data sets.
Thank you, Daniele. You replied, I think, also to the second question, that is, how do the quality and resolution of multispectral data impact the accuracy and representation of the final 3D model? So maybe I've already replied for a while. If you want to add something about this.
Yes, I mean, also the quality of the instrumentation affects on the final result. The photogrammetric process works mainly using pixel, as data. So the higher is the quality, is the image is generated, and the better is the result. Of course, there are limitations. Of course, there are some precautions to take, but using a quality camera, quality flashes, and filters affects on the final result. Of course, maybe using a better top professional camera for the UV acquisition could have generated a better geometry. But of course, integrating RGB with UVL allowed us to guarantee high quality geometry as well. So it depends on many factors. In our case, since we had to to rely on the available instrumentation, we had to find solutions in post-processing. So this is one possible workflow, of course. There are other workflows already published. It depends on the environmental condition, setup condition, available instrumentation, but of course you can find solution to overcome this limitation.
Sure. Sure. Thank you so much for replying in details like this. Let me add something about the environmental condition. We, you know, that we had to move many times the statue to have all the photogrammetric campaign and the diagnostic campaign. But one of the main issue inside the museum is that normally it's not that easy to move statues to have a perfect environment to do photogrammetry or multispectral diagnostic. So this I think that this workflow may really let understand museum professional of how environmental conditions when we have diagnostic, for example, or digitization are fundamental. And this isn't a secondary aspect; it's a primary aspect when we work in this kind of, and we want to obtain this kind of result. There's a question again for you from Sofia Sotiropoulou. You presented the manual UV mapping for the Bikini Venus case study. What does each UV texture island represent?
Okay, so here I have in Blender the statue. So the UV islands are part of the geometry associated with the texture. So I show you here briefly. So here you have the texture. Here we have the 3D model. So if I select this area here, this area in the 2D space corresponds to this area in the 3D model. Okay, so every single part of every single island in the 2D space are associated with specific part of the model. So this subdivision was done manually in order to better control the final result. Why? If I show you the original mesh, the one textured mesh generated by photogrammetric software, you can see that the UV mapping generated by automatically, but the software is very noisy, is very fragmented, okay? And it's almost impossible to manipulate or to adjust it in post-processing. So in order to, for example, to intervene in the final texture or in the final model, it's preferable to handle this UV mapping, the process of unwrapping the geometry on a flat plane manually. In this way, it's possible to better control it. Of course, it's not possible when the geometry is too high. So it would have been almost impossible to do it manually with the original model composed by 28 million of polygons. But reducing the number of polygons and converting the triangular mesh, this one, into a quad-dominant mesh, using retopology tools, it was possible to generate an ad hoc UV mapping that allow a better control. And not only allow a better control, but also it's possible to keep this UV mapping for all the spectral textures. So if we check, for example, the UV mapped model, as you can see, the UV mapping is the same. Okay, I can change the texture, and you can see that That's the coordinates, the UV coordinates are always the same. And so these allow us to maintain consistent UV coordinate among different 3D models.
Thank you, Daniele.
It was clear.
Yeah, sure. Thank you, Daniele. I've got a question for Bruno. Since you were talking about Perceive project is AI oriented, but you talked about the atlas, and you stated that the segmentation has to be done in a sort of way manually. So what do you think that could be in the future, the support or the help of AI in this sector?
Yeah, so in general, there are several possibilities, I think. And of course, there is all the possibilities related to the segmentation, semantic segmentation. But of course, this is something that is come as a support. So supporting at macroscopic or mesoscopic level, and then there is also the human intervention or in the process. So there is something that AI can support in terms of accelerating or facilitating specific tasks. But then, of course, there is also the human intervention at some point, especially in this field.
Thank you, Bruno. There was another question about what Giorgio was asking if the Venus actually emit visible induced fluorescence. I asked Donata Magrini to reply to the question, and the question is done, because you can see all the replies and the conversation between Giorgio and Donata on the chat. Since we have other questions from technical point of view, I didn't want to change your attention to diagnostic side. Another question, of course, congratulations for the beautiful work and for offering this useful comparison. What type of targets were used to calibrate UVL and VIL images? How were the metalness and roughness maps derived from the diffuse map? Did you perform across polarization? Last, it is currently possible for other institutions to implement your platform on their own local servers.
Okay, I can answer part of this question. Okay, in this case, the metalness and roughness were derived from the diffuse map using a specific tool called Materialize. It's a free tool that's allowed to using parametric function to convert the diffuse map, the color map, into metalness map and diffuse map. Since in this case, since the difference between the marble and the gilding was really evident in the diffuse map, the software didn't have any problem in recognizing the different materials, so it was pretty easy. We didn't use cross-polarization on the field. We using diffuse light and soft light in order to smooth the environmental light condition. We avoid reflection on the gildings. Of course, it was impossible to completely eliminate the gilding effect, but using masking, we obtain at the end we obtained. I can show you here the final texture are almost without reflection. Okay, So we try to remove in post-processing the reflection on the gildings, and we simulate using the metalness those reflection in a realistic way using PBR. Of course, using polarization filter directly during the acquisition would have probably improved the final result. But as I said, we did the acquisition in two different moments, and so at the beginning we didn't know how the 3D model would have been used in the future when we captured the 3D models. So that's why. So we had to do a lot of post-processing in order to optimize as you have seen using Blender, in order to optimize the texture for real-time implementation.
Thank you. And then Bruno, do you want to add something?
Yeah, I can answer the last question. If it's currently possible for an institution to implement your platform on their own local servers, absolutely yes. There is the Atom framework is open source under GPL 3 license, so everyone can use the framework and install on their own server. There is also on the website, there is also several tutorials. It's actually pretty easy to have an instance of Atom up and running. And then there is this plug and play model offered by Atom for vertical application. Like in this case, MuLaX is one of the vertical applications. So once you have the an Atom instance up and running, it's actually very easy to include a specific application or multiple application on your own instance, like MuLaX or other tools, and then they automatically work. So it's quite easy. You can find all the information on the website, or there is also the open group, international open group on Telegram.
Thank you so much. Let me add just an information. Of course, MuLaX is one of the aim and is a key point of Perceive, but we are also working on a repository that will be happy to have the collaboration of all the institutions and museums that are engaged, of course, professionals that are engaged in this kind of research. So this is not only about MuLaX, but it's about all the projects, all the Perceive. The collaboration is very welcome, and as soon as we will publish our repository, this will help us to create a very big community working in this field. So all the sharing of the data will be welcome and hopefully kindly requested. So the same thing for MuLaX will be for the repository. We will have a specific episode of the webinar detailing what is our repository, how it works, and how people can contribute to this. So please stay in touch. I thank you and thank Daniele and Bruno for your very amazing presentations. Just a few words to remind you about the 17th of June. We will have at 11 a.m. Rome time, the 4th episode of the webinars. It will deal about the orthogram, revolution and realities. The speakers will be Giorgio Trampi, Associate Professor at the Norwegian University of Science and Technology, and Kathleen Langford, Curator, Writer, and Researcher specializing in photography. If there are no more questions, let me check again. A wonderful presentation, many thanks. So you can read the comments with the congratulations for you both. Hopefully follow us on our social media website, and please subscribe to our newsletter to be updated with all our initiatives. Thank you so much for participating. Thank you, Bruno. Thank you, Daniele.
Thank you so much.
Bye.